how to create this TBT. Okay. So I hope the screen is visible. The PPTs are visible. So we have seen that in the BST or in any binary tree, the number of nodes, uh, if they are n, then there will be n plus 1 null nodes. Okay, that means we are wasting the memory in storing the reference to null nodes. And also for traversing the tree, we are using extra memory for stack or queue. We have seen the algorithms for that. Non-recursive algorithm for in-order, pre-order, post-order, in which we used stack object, whereas in level-wise display, we used the queue object. Okay, so we are using the extra memory in order to traverse the tree, and it also takes time to switch the nodes, to push the nodes in the stack or queue, and to remove the nodes from that data structure. So that time will also be more, switching time will be more if we have various data structures in our particular program for traversing. Okay, and traversing is done many times, so this will be inefficient sometime. Okay, if we have to traverse the tree more times, more number of times, then these methods which we are using, they can be ineffective. So in order to prevent all these things, we can utilize the memory which is there for null nodes for traversal purpose. Okay, so the null nodes which are there in the tree, those will be utilized for traversal purpose, so that these nodes will point to in order predecessor or in order successor. Okay, if it is the left null, then we will ask it to point to in order predecessor node. If it is the right null, then we will ask it to point to the right, that is in order successor node in the traversal. Okay, so the class node is modified in this way. The node memory for the node will be modified. Instead of just storing data and left right child pointer, we are also storing the flag. Okay, the flag that is left thread or right thread. This is the flag which will tell whether this left thread is a flag which is telling whether this left child is actual node, pointing to actual left child node, or it is a thread. Okay, similarly, this right thread, it is a flag which will tell that this right child, this pointer, is pointing to actual node, or it is pointing to null. Okay, so our thread is modified in this way. Oh, just wait for a minute, I'll come back. Hello, sorry for the break. Okay, so this is the initial structure of the thread. Now we have modified the node of the tree in this way. We have added two more boolean values, okay, or integer values which will be storing the status whether this left is pointing to actual child or it is a thread. Similarly, right is pointing to actual child or is it a thread? Okay. So root, see this tree which is now modified, there is no null node. If you see here in this tree, there is no null node present. Okay, so all these nulls are modified to the threads. See here, this is the root node. Actually, this is the dummy node. Okay, and actual root is present to the left of the dummy. This is the structure of the TBT, where the dummy is the initial node. This is our dummy node, which is to its left. Our actual tree's root is present. Okay. Okay, this is the dummy node, and this is the basic initialization of the dummy node. This is the root node, actual root of the tree, and if the left child is present, then this flag will be false. Okay, this flag is telling that it is actual child, left is actual child. Similarly, if right child is present, this flag is false. Flag is false. And see here, this B is also having left child, right child. That's why both the flags are false. This is also having both the children, left, right. That's why both the flags are false. Now, see here, for this E, there is no left and right child present. That's why the flag is true now. And this left and right pointers, they are not pointing now to child, they are pointing to the in-order predecessor. This left is pointing to in-order predecessor, which is B, and right of it is pointing to in-order successor, which is E. Okay. Similarly, see this node I, its left is pointing to in-order predecessor, which is D, and right is pointing to in-order successor, which is B. Are you getting? There is no null node now. Okay, this left and right, which might be null in the BST, they are now converted into the threads, which are for the in-order successor and predecessor nodes. Okay, so this is the threaded binary tree, in-order threaded binary tree. Why it is in-order threaded binary tree? Because these threads are pointing to in-order predecessors and in-order successors. Okay, that's why it is in-order threaded binary tree. Are you getting? And the leftmost, this node, its left is pointing to the dummy node, and the rightmost node's right is pointing to dummy node. Okay, and this is the structure of the dummy node. To the left of it, the root is present and right is pointing to itself. Okay, right is pointing to itself. And this is the standard structure of the TBD. This diagram is from the Horowitz-Sahani book. If you have any doubt in this structure, you can ask. We will see how to use these threads for traversal purpose and how to do the traversal in different ways. But are you getting the modification in the structure? At least the structure is clear of the TBT. Okay. So here all threads are all the null pointers, they will be converted to the threads, which are nothing but the pointers to in-order predecessor or in-order successor. Okay. And this is the standard structure of the threaded binary tree. This is the dummy node to which left of which actual root of the tree is present, and traversal starts from this. Okay. And so we have to do dummy left in order to start the traversal. And the leftmost left thread is pointing to dummy, rightmost right thread is pointing to dummy. This is the standard structure present. Okay, and this is the initialization. When the tree is empty, we will have this dummy node whose left is pointing to itself and right will also point to itself. And when we are putting the first element, when we are inserting the first element in the TBT, then this left of dummy will point to that root. Okay, so instead of pointing to itself, it will be pointing to the root of the tree, that first node which we have inserted. And right will be as it is, always. Okay, are you getting modification in the node structure as well as modification in the tree? So this can be a BST, this can be any binary tree, or this can be the expression tree also. Okay, any tree, binary tree can be converted into the threaded if we are utilizing its null to point to in order predecessor or in order successor node. Okay, so this is partial threaded binary tree which is shown here, in which only right null pointers they are converted to the threads. If there are some doubts, we can go for it. Do we have to create a dummy node for every tree? Yes, we have to initialize the dummy node, and then we can start inserting one by one node into it. Yes, this dummy will tell us where to stop. As we have seen, the leftmost thread is pointing to dummy, and rightmost node's right thread is pointing to dummy. Okay, so there is always dummy node. This is the standard structure given. Then Rohit is asking, can't we have point the previous node for a leaf node without boolean? No, boolean is there. This flag is there which will tell us whether the left is pointing to actual child or it is pointing to the success in order successor or predecessor. Okay, in order to come to know that, there should be a flag value. Okay, so that is required. That's why modification in the node is required. Pranav is asking, what is the use of thread connecting the dummy and leftmost node? Yes, this will tell us where to stop. Otherwise, we will go on. See, there is no null node present. In BST, when we stop, when we reach to null, that will tell us that yes, we have to stop now. But here there is no null present. So if we reach to null, this dummy node, while accessing the nodes, okay, we'll see those traversal algorithms for TBT. And this dummy will tell us where to stop. Okay. Yes. We can go ahead. Okay, this is the partial TBT where we can uh, just check that only right half of the nulls, they are right nulls are converted to threads. Okay, and this 13 right also should point to dumb. Okay, that is also a thread which should point to dumb, and that will tell us that here we should stop. And if we traverse this, okay, just we will try to traverse this. We will start from 6. Okay, suppose I have to traverse, this is the BST. Yes, this is the BST which I will be traversing using the Inorder Traversal algorithm. Okay, but I will now modify my algorithm a bit. I will move to the leftmost and start traversing from it. And here I will find that there is no left child. Okay, and so in this case, if this is the partial TBT, okay, I will check the right. Right is not a child, so I'm not now having stack. Even I'm not using recursion, but I will have the condition whether right is a child or it is the thread. Right is not a child, it is a thread. So I will follow that thread to reach to my parent, that in order successor node. Thread is taking me to the in order successor node. Okay, so using this thread, I will access the successor and again I will continue. Now the right is child, I will reach to that child and leftmost of that child, but this is the leftmost only of this right subtree. Okay, and its right is again a thread, so I will follow that thread. So see here, I have started from 6 and I went to 1 because it is the leftmost, and I started traversing from this leftmost. As I'm doing the Inorder Traversal, I will first reach to leftmost and then I will check what is right of this leftmost, whether it is actual child or the thread. If it is a thread, I am following it. Okay, and then I will display this also. I have displayed 1, I have displayed 3. Then I will move to right. Right is a child, and leftmost of that right, which is 5 only, then I will display 5 and follow the thread. Then I will display 6, and then I will move to the leftmost of right, that is this 7. Then I will display this 7, follow the thread, display 8, then right leftmost, that is 9, display 9, follow thread, display 11, follow right. Okay, like this I will continue till I reach to dummy, and I will stop now. So no need of stack, no need of recursion in order to traverse this. Traversal is simplified. So we are putting more efforts on creation of the tree, but traversal is simplified because of it. Okay. So we start at the leftmost node in the tree, print it, and follow its right thread. If we follow a thread to the right, we output the node and continue to its right. If we follow the link to the right, we go to the leftmost node, print it, and continue. Okay, so we have to start traversing from leftmost in order. Leftmost will be displayed, and we are following the right thread. If right is a thread, then we will output it. Otherwise, we will follow the link, right link, and leftmost of that right. Again, follow the thread. Okay, this is the simplified algorithm. So see here how the execution takes place. Start with 1, then thread will take us to the successor, which is 3. Then right is a child, leftmost of that right is this same. Then follow the thread, again leftmost of right, which is 7. Again follow thread, leftmost of right, which is 9. Follow thread. Okay, like this. Okay, so even with the partial TBT, we can get the Inorder Traversal. And if we convert the other left nulls also into the threads, that will give us, in the reverse order we can move. Okay, we can move to the uh, predecessors also. Okay, so we are still wasting pointers. Still half of our leaves are null. We can add threads to the previous node in Inorder Traversal as well, which we can use for traversal in the backwards way. Okay, or to do the post-order traversal also. Those predecessors are required. So this is the complete. And here it is that dummy is not shown, but it is always there. Okay, and our root, this 6 is attached to the left of the dummy, and its leftmost is pointing to dummy, rightmost is pointing to dummy. Okay. Now we can check the tree has 9 nodes and 10 links, which have been replaced by threads. Now these 10 nulls will be replaced by threads. If we traverse the tree in inorder nodes, in inorder, nodes will be visited as, yes, that was for the previous tree which we have seen, that BDCE. Okay. We have covered all these points. Okay, so memory representation of threads. is must to distinguish between actual pointer and thread. This can be done by adding extra bits in the node structure, which are the flags. So these are the actual links, left and right, and these are the flags here. Okay, left L bit and R bit here. You can take any name for these flags, and this is the data. Okay, so it is my uh, assumption that L bit of a node will be 1 if left child is normal, otherwise it will be 0. 0 means if L bit is 0, it is a thread. If L bit is 1, it is the normal link child. Okay, so we can create the BAs and convert them into the threaded binary trees. Okay, so all of you can try creating the trees for this and showing the threads also. Okay, after the TBT is created, then we have to traverse it. First, we will see how the traversal is done, and then if the structure is clear, you can create the BST and you can convert it into the thread. Okay, so creation we will observe afterwards, but we'll see the traversal algorithm first in detail, how the traversal will be done. Okay, if the tree is created, we'll assume that TBT is ready. You know how the TBT will be now created. The structure is clear to all. And now we can go for the traversal. The pre-order traversal, or first we'll go for in-order traversal. Okay, in-order traversal of a TBT. If the right child of the node is not a thread, then the leftmost child in the right subtree will be the in-order successor. So we have to go to the stepwise. Okay, we will see what will be the different conditions. If I have to traverse a threaded binary tree in in-order way, then that particular node can have the left child, it can have a right child, or if not the child, it will have the threads. Okay. So first is in order traversal, we reach to the leftmost node and we start traversal from that leftmost. Isn't it? So we will see that that leftmost node is having a right child or right link. It is having a right child or it is a right thread. Okay, so we'll check flag for that leftmost. We'll display that leftmost and then we'll see the flag value. So if it is telling that right is a actual child, then we will move to the leftmost of that right child. So that will be the in order successor, which will be displayed after this particular node. And if not, if right is a thread, then we'll follow that thread to reach to the in order successor. Okay. So if right is a thread, then the thread itself points to the successor. So we can reach to that successor using the thread. And if right is a having actual child, then we will move to the leftmost of that right child. That will be the in order successor. Okay, so these are the two conditions in order to find the in order successor node of a particular node in the TBT. Okay, and if we follow these conditions for every node, okay, here suppose we have to find the in order successor of a particular node P, then we'll see we will write different conditions for it. Who will be the node after P? Okay, if we are currently at node P, who will be after P? We have to check its right link, whether it is a thread. So we will be checking the flag. R bit is 0, that means it is a thread. Then return P right, that will be the successor. So we will return that successor. P right is a successor node. Okay, that means it is a right thread which is a successor. After P, that will be the next node which is displayed. Otherwise, if P R bit is not 0, that means it is 1. So we will move to right of that P equal to P right, and leftmost of that. Okay, so until P L bit is 1, that is left is child, till that time we are saying P equal to P left, that is leftmost of the right subtree, and that will be the successor node. So return P. Okay, for these two conditions which we have seen, we have written this function. Okay, so if I am currently at P, who will be next to P? Either if it is P right is a thread, then we will follow that thread. This will be done. If P right is actual link, then we have to move to that link and leftmost of that right. That will be the successor. Okay, that will be the node which will be followed after P. Are you getting? And if this inorder successor, it is called in this particular function, this will give us the traversal. Okay, so this function we will call from our main function, which is taking help of this successor function. What this function is doing, initially we have to start the traversal. Okay, so this T is nothing but our dummy node. Okay, the reference of our tree, which is dummy. Okay, head equal to T, which is dummy, and T equal to T left, because this is the actual root of our class. So we have to move to the left of dummy, and then as Inorder Traversal, it starts from the leftmost. Okay, first we will move to that leftmost until T L bit is 1, that is actual child. We are following that T equal to T left, T equal to T left. This will take us to the leftmost of our tree, from where we have to start the Inorder Traversal. Okay, and while T is not equal to head, that is our thread is not a dummy, we don't reach back to the dummy node, then display the data and follow the successor node. Follow the inorder successor, which we have seen. Okay, this function inorder successor will be called. Are you getting where we are using that dummy to stop the traversal, to stop finding the inorder successor? Okay, so while T is not null, T is not head, again we are displaying that successor's data. Okay, and finding the next successor, next follower of, by using these two conditions. Any doubt here in order traversal? If you have understood in order traversal, in the same way we have to write the pre-order traversal also. Are you getting how the thread is used? Here you can see in this particular function, there is in this particular function we have not used any stack, we have not used any recursive call, still we are doing the traversal using thread. Are you getting? Okay, that is the advantage of TBT. So for creation of TBT, you need some logic. You have to send. And the one more disadvantage of this TBT is extra memory is required for storing those flags in the node. Okay, there are two flags which we have to use with every node, which will tell whether that left is pointing to child or a thread. whether that right is pointing to child or thread. Is this much clear? Shall we go to the give an example? Okay, fine. So we have seen this function, this particular tree, isn't it? This we have seen in order traversal. So in this, what we are doing in order traversal, see, first we have moved to the leftmost. Okay, so okay, we have moved to the leftmost. That was our first step in order traversal. We start from dummy. Okay, so there is dummy present here, and we have to reach to root, which is present to left to dummy. So we said that t equal to t left. Okay, so that takes us to the root node, and from root we have to move to the leftmost. As we want to do the inorder traversal, we are moving to the leftmost, and here we are checking. We have these two conditions for finding the successor, inorder successor, which will be displayed after one. Okay, either right is a thread or right is a actual child. Here in this case, right is a thread. So follow that thread, that will be the successor node. So 3 will be displayed. Okay, you can see the output 3 is displayed. Now here in this case, right is not a thread, it is the actual child. So leftmost of that right child is the successor node. That means 5 left is also null. That means in this right subtree of 3, this 5 only is the successor node. It is the leftmost node of the right subtree of 3. Okay, so 5 will be displayed. That will be the successor. Again, right is a thread. So follow that thread, that is taking us to the successor. So 6 will be displayed. In this case now, right's leftmost is the successor node. That means this 7. Okay, so 7 will be displayed. Again, right is a child. So follow that thread, that will take us to the successor. Display it. Again, right subtree is leftmost. That will be the next. Okay. Again, right is a thread. Follow that thread, that is the successor. That will be displayed. Then leftmost of right, that is 13. That will display. And 13 right is a thread which will take us to dummy, and we will stop finding the successors. Okay. Are you getting? So this is our inorder traversal function, in which we start with dummy, and dummy left is root. So t equal to t left will be done, and then we have to reach to the leftmost node. That's why this loop is written. So until left is child, we are moving. That is left. L bit is 1. We are moving to left, left, left. Okay. And then we start this loop for finding successors. Until we reach back to dummy node, we continue finding successor node. Okay. And displaying that successor node. Find in order successor, that we are doing continuously. Okay. And that is done with this function. In order successor is found with this function, with these two conditions, whether right is a link, right is a thread, or it is the actual link. If it is a thread, return as it is. Okay. Otherwise, if it is the right is actual child, then leftmost of that right is the successor node. So we are moving to right, and leftmost of that right, that will be returned. Okay. So these are the two conditions which we are following for finding the inorder successor. Okay. Is the inorder traversal clear? Can we move to the pre-order traversal? Pranav, is it clear now? Okay, fine. Similarly, in pre-order traversal, we start traversing from root itself. We display the root itself. And remember, in pre-order traversal, the left child is the successor. Okay, if a particular node is having left child, that is the successor node. That is the node which will be displayed. Okay. Okay, we'll see this afterwards. First, we'll discuss that pre-order traversal. So in pre-order also, we have to start from root. That's why head equal to t. This is nothing but the dummy node, and t equal to t left. Okay, t equal to t left, which is taking us to the root, and we will start displaying from root. Root will be displayed first in pre-order traversal. Okay, while t is not head, that is we don't reach to dummy node again. What we have to do, we have to start finding the successor node. Pre-order successor here is found. Okay, it will give us the pre-order successor. Even if tree is constructed for in-order nodes, we will be finding the pre-order successor. Okay. And here we are not moving to the leftmost because in order is started with the leftmost, but pre-order it starts from the root itself. So we'll display the root itself and find its pre-order successor. And in case of the pre-order traversal, the left child will be the pre-order successor. If a node is having a left child, that will be the next node which will be displayed. Otherwise, if it is not having the left child, if it is not having a left child, then it's see that particular node is displayed and right child is the successor. Okay, so this is the case. This is used to find the pre-order successor of any node. So if L bit is 1, that is normal left child, that is the successor node. If L bit is 1, then that is the successor node, that is actual left child. Otherwise, if left child is not there for a particular node, if left child is not there, then we are checking for the right child, whether right is actual link or not. Okay, but suppose R bit is 0, that means it is a thread, that means right is also not a child. Then we have to just climb one step up and it's we have to move to the right subtree of the parent. That will be the pre-order successor. So we have to climb up. Okay, this is the step. While p r bit is 0, we have to move to the right subtree of the parent. That will be the successor. Okay, so we'll discuss one example for pre-order traversal. The same example we'll discuss, same tree here. Suppose we have to traverse now using pre-order. Okay, so we'll start from 6, the root, and its left child will be the reorder successor. That is after 6 we are displaying 3. Its left child is the successor, which is actual node. Okay, so this will be the pre-order successor. So how we are going to display 6, then 3, then 1, until left is a child, actual child. But in this case, left is not actual child, it is a thread. Okay, so what will be done? In this case, who is the successor of this? We know the pre-order traversal, isn't it? So after 1, 6, 3, 1 are displayed, we have to move to the right subtree of parent. So we will be using the right thread to reach to parent, and then its right will take us to the pre-order successor. Okay, again here left is not a child, so we will use right thread to reach to the parent, and its left its right will be the next successor node. After 5, 8 will be the successor, okay, which is present at the right, this successor's right child. Okay, so we are following this thread once and its right child. That will give us the pre-order successor. Again, the left is actual link. So we are moving to left. This is the successor of 8. Again, right is a thread. So it is taking us to this 11. Right is a thread and its right child. It is the successor of 7. Again, 9 is the successor of 11 and 11 right. This 13 is the successor of 9. Are you getting? So in order to find the pre-order successor, we have two conditions. Either left is a child, so that left child is the pre-order successor. And when left is not having the right, well, left is not a child, it is the thread. We are following the right thread in that case. So we have reached to the leftmost. When left is not a child, that means we have reached to the leftmost of that subtree. Then we have to follow the thread once and move to its right. Okay. Again, this is the leftmost of the right subtree. Follow its right thread. It will take us to the parent and its right subtree. Again, left, left, left. Again, follow thread. Then move to right and its left, left, left. Are you getting? We'll see one more example. Suppose we have to do reorder traversal on this tree. Then we'll start with A, that is dummy left. Okay. A will be displayed. Then its successor, pre-order successor is B, as it is actual child. Then B also has actual left child, which is D. So D will be displayed. Again, D is having actual left child, which is H. That will be the successor. H will be displayed. Okay. Now this is not having actual left child. It is a thread. That's why we will follow the right thread. Okay. That is this D and its right child. That is I. This I will be the successor node. Right thread's right child will be the successor of this H. Again, I left is null. I left is thread. That's why we will follow the right, which is taking us to B and E. Okay, right thread's right child, that will be the successor. So E will be displayed after it. Then this is also not having left child. So follow right thread, which is A, and its right child, which is C. Okay, so after E, C will be the successor node. Then left is C is having left child, which is F. That will be successor. After C, F will be displayed. Again, right thread's right child, which is G, that will be displayed. And again, right thread will take us to dummy and we will stop. Are you getting? Pre-order traversal as well. Is the pre-order traversal clear? So in pre-order, we start from root, that is this T left, dummy left, and we start finding the pre-order successor using these two conditions. First is left is a normal child, so return that P left as it is. That will be the successor. And second condition is if P R bit is 0, that is thread, follow that thread. Okay, follow the thread. P equal to P right and its right child. Right thread's right child will be the successor. Okay. Any doubt? So is in-order and pre-order traversal, both the methods clear? We are not having post-order traversal in our syllabus. Okay. Clear? Now how to create this TBT? Shall we see that so that our first unit will be over? If we complete this creation, and we can discuss during the lab in detail. Okay, so we'll just go through this particular example. This is also taken from the Horowitz-Sahani book, these diagrams. And all these algorithms are also from the Horowitz-Sahani book. In that, this uh, tree, all the trees or TBT is given in very good manner in the Horowitz-Sahani book. And PhD you can study from the Horizon, because the algorithms which we referred are from Horizon. It is the examples etc. are given very properly in that. And I have also uploaded those diagrams or the algorithms for BST deletion, creation, etc. on the Google Classroom. Okay. So here, see various conditions of inserting R as right child of S in the threaded binary tree. Okay. So suppose we have to insert R in the this previous threaded binary tree. Okay. We will be following the insertion algorithm. In the TBT, if we have to create the TBT, we will follow the insertion multiple times. Like we did in the BST also. We called multiple times insert, which returned us the properly created BST. Okay, similarly here, we have to insert a particular node, suppose R, in the previous TBT, which is in this way. It is created in this way. This is our root, then this is the node S, and this is the particular node, and its left thread is pointing to this, its right thread is pointing to S, and we have to insert this R now. And this R is to be inserted as a right child of S. Now, what will be the different statements? Okay, if we have to insert as a right child, R is to be inserted as right child of S, then uh, see the right thread of this will be copied as it is here. Okay, right thread will be copied as it is. So R right will be equal to S right. Okay, because as currently S is pointing to this suppose dummy node, then R should point to this node. Okay, and this R is to be R should be the right child of S. So S right will be R. Okay, first we will copy in R right S right as it is, so that this will point to this node, and S right is equal to R. Okay, and what will be the left of R? Left of R is this S, because it should be the predecessor. Okay, so these three things we have to consider. First of all, copy this right thread value into R. Then, just a minute, I have to take a call. Continuously, I'm getting a call. You can go through this diagram. First diagram. Hello. Sorry for the interruption. Okay, so if I have to insert R as the right child of S, then I will copy this thread value as it is. That is, S right will be copied as it is here in R right. Okay, and then I will say S right equal to R, and in the left of R there will be S. So R left is equal to S. Yeah, these will be the three things which we will do in order to insert R as right child of S. If we have to insert R here, Mm, this is suppose before and this is the after. That means in between this we have to insert. Then S right is equal to R and R left will be S and R right is equal to S right. Okay, the same thing. These three things which we have done. So our tree will be enhanced by doing these three things. We have to copy right as it is from the parent node, and uh, to the left we will copy we will point parent only. R will be first copied as it is to the child from parent, and its left will be pointing to parent itself. And then parent right is equal to child. These three things we will do. The traversals we have already seen. This is the application. These are the various applications of trees, and I'll just share one document. You can go through these applications. Class hierarchy in object oriented programming, that is done using any trees. File systems, for that also trees are used. Storing hierarchies in organizations. Expression trees, which we have seen in detail. Huffman trees, they are also example of or application of trees. Then games. In artificial intelligence, you can see a lot of various types of trees, other than what we have seen. Other than that, various types of trees like a star tree, etc., are used. Okay, and I'll just share one document in order to see the TBT in the example of TBT, which we have already seen. The structure of dummy node, initial structure of the dummy node, and this tree also we have seen discussed. Then in order successor, this insertion also. Now insert right function. In order to insert a node to the right, what things we are doing? We are copying the right as it is from the parent. So we are copying the right thread also and right pointer also. Isn't it? So when we are copying this from the S right, this particular thing to this R, that means we are copying the thread value also and the flag value also. Okay. So both the things we will copy, the flag as well as the value. Then we are asking the left to point to parent itself. So our left will be pointing to parent itself, that is S. So our left child is S, this particular thing. R left is equal to parent. Okay. So both this R right and R left are initialized. Now we have to attach this R to S right. Okay. So S right is equal to R, the child, and S right is equal to false, because this is actual child which we are attaching to S right. Okay. Are you getting all these 6 statements? There will be 2 statements for copying every link, because we are copying the thread, the flag as well as that particular value of the pointer. Okay. So using this, we can do the insertion. Similarly, if we have to insert a particular node to the left of the parent, okay, suppose we have to insert a particular node to the left of the parent, then we will be copying the left as it is from parent. Then right will be pointing to that parent, and that node will be attached to the left of the parent. So exact reverse we will do while doing these 3 things. Okay. So we have to write the similar thing when we have to insert a child to the left of the parent. Instead of copying from right, we will be copying from left. Then child will be the right. Instead of uh, attaching to right, we will attach to the left. Okay, and the right will point to the parent. Right thread will be pointing to parent. So we will be following this algorithm in our insert function, which we will see during the lab. Okay, that function we will see in the lab in detail. But I hope this is clear to you. This algorithm is clear to you. Remember this diagram. This will tell everything. How the insertion is done in the table. If you have any doubt, please ask. We will get more clarification during the lab.